My name is Brian Call. I'm the manager of the Yale Quantum Institute. Thank you so much for coming here for this program, for this summer program of the Wright Lab and YQI. Today we have the chance of having Yongshan, who's an assistant professor in computer science and also a YQI member, who's gonna walk us through an introduction to quantum computing. So we'll have the chance to code for some of you, maybe for the first time, and we'll follow this. Thank you very much for doing this.
Thank you for inviting me. All right, thank you, Florian. It's a pleasure to be here. As Florian mentioned, this 2-hour session will be broken up into 2 parts. The first part is a lecture, 1-hour lecture on what happened if you allow quantum science to meet computer science. And the second hour will be hands-on programming exercise. Let's get started. I would like to speak about the amazing benefits, both scientific benefits and technological benefits of bridging quantum science and computer science. I want to say that before I talk about the bridges, let's just take a moment to appreciate the technologies that these 2 scientific fields have brought us. Quantum technologies have brought us lasers, MRI technologies, atomic clocks, GPS systems, global positional systems, transistors. They all rely on our understanding of quantum mechanical behavior of different systems. And the theory of computing also have brought us amazing technologies. We are using smartphones, computers, internet, artificial intelligence. Sounds like we are really enjoying the benefit of studying these 2 fields in isolation. But what if we bridge the 2 fields? What kind of new technologies does it bring us? This is the topic of this lecture. As a scientist, though, I'd like to ask a more concrete question rather than predicting what will happen in the future. Can we control atoms to compute? I'd like to also say that you might say, well, aren't we already doing it? Right? The computers are made of atoms, and we're using them for doing computation. But I really want to emphasize that when we say control atoms, we want to say it's about the quantum mechanical behavior of the atoms that we want to take advantage of for computation. And when we think about computation, we think about how to make it more efficient. And this question would not make much sense only a few decades ago. I think it's an exciting time. We live in an exciting time that we're able to ask this question. But before we delve deeper into this question, I also would like to acknowledge that if you ask this question to a different audience, they're going to have different reactions. If you are a theoretical physicist, then you will think about the fundamental limits of what is the laws of physics that will govern this complex quantum systems that will maybe allow us to compute certain mathematical functions. Is there a limit? If you ask experimental physicists, they will say, challenge accepted. Let's make some atom, find a natural atom, or make some artificial atoms to engineer the Hamiltonian how system interact and make them programmable. So some parameters you can tune, some knobs you can turn to perform computation. And if you ask theoretical computer scientists, then you would say, from the algorithmic perspective, does it gain us anything? If you are allowing quantum mechanical operations in an algorithm, does it solve problems more efficiently? That's a notion of quantum advantage. We'll speak more about that in a second. And if you're computer systems engineers, you will say, well, is there anything we learned about building classical computer that we can borrow or inspire to scale up quantum systems for computation? So a lot of interpretation of this question, but this is also the theme of the talk. Quantum computing is a interdisciplinary field by nature. We cherish this interdisciplinary nature. There's no way to make a talk that will make everybody happy. So I try to make some abstractions about physics, some abstraction about computer science, and then emphasize on the point that will make the bridge between the two. So at the fundamental level, what are we studying as a scientific question of how to control atoms for computation? Well, you would say laws of physics governs everything that we do, including building a computer. So if you follow certain laws of physics, namely allowing certain operations in your machine, that will translate to how efficient you can solve certain problems. If you, for example, allow only deterministic moves about transforming information, manipulating information, then you arrive at a deterministic algorithm. There's a class of problems, computational problems, that you can solve efficiently with a deterministic algorithm. People have noticed that if you allow randomness in algorithms, in your steps of the computation, such as flipping coins, or shared randomness between two parties, then you arrive at something called a randomized algorithm. And it's amazing to me that including randomness in an algorithm actually gives you a boost in the set of problems that you can solve efficiently. So the class of problems that you can solve is a superset to deterministic algorithms. So people wonder, if you allow operations in an algorithm to include quantum evolution, maybe quantum mechanical laws of information, you arrive at quantum algorithm. Does it give you a bigger set of problems that you can solve efficiently? The goal is to find what is in there. What are the problems that we can solve efficiently that we couldn't before? So again, if you are a theoretical physicist, you will maybe think of the limit. Is quantum computer a machine that allows quantum mechanical operations? A universal machine that can simulate all laws of physics, like atomic systems, complex quantum systems. Can you describe the evolution of a quantum system using operations in a quantum computer, in a controllable quantum systems? So this goes both ways. Laws of physics determines what you can do, and the machines that you build based on those laws of physics can allow you to describe or simulate physical systems. And I think it's an amazing bridge of how physics and computation actually comes in together. So I'd like to put my computer science hat on for a moment and talk about computational hardness and motivate what are the problems, again, that a quantum computer will allow us to solve. Some problems are harder to compute. And when we say hard to compute, we mean exponential resource, either in space or time. When we say space, maybe you need to store exponential amount of information, or it will take exponential number of steps. And a prime example that I want to show is the primality testing. Test if a number is a prime or a composite. And it is well known that there exists a randomized algorithm that will solve this problem very efficiently. But if you only use deterministic algorithms, it's unclear how you can solve as efficiently. So adding randomness in algorithm can give you a boost in terms of efficiency. Similarly, Peter Shor in 1994 noticed that if you allow quantum subroutines or setting up qubits, quantum bits to perform computation as a subroutine in an algorithm, this can also give you a boost in terms of solving prime factorization algorithm. This really sparked the field to look into the computational power of complex quantum systems. And I also like to motivate the field of quantum computing from this early sort of essay or comments from Yuri Menon and Richard Feynman. So this is only a quote, but it describes the essence of why we would like to build computers made of quantum mechanical objects. Because if we want to simulate a quantum mechanical system of many particles, we're going to need an enormous amount of classical information to fully describe the system. And it's unthinkable, even assuming that classical computers will get more and more powerful, which we'll talk about in a second. It's unthinkable to use the sheer amount of information that you need to store and the sheer number of steps you need to simulate on a classic computer is physical. So this is a motivation to study how to build a quantum mechanical system to solve computational problems that are inherently quantum. So I spoke about computational tasks, but they exist both in classical world and quantum world. So I mentioned that the limit of classical computers, but are we happy with today's computer? They seem to get better and better every year, and many of you might be familiar with the empirical Moore's law, which describes how there are different variants of it, but roughly describes how much transistors we can pack cost effectively on the chip over the years. And there is exponential growth. This is the log scale and vertical axis. Year by year, the cost for building transistors on a chip gets lower and lower. But there's a limit. So Moore's law really hit the wall right around 2000. And this is because many of the fundamental properties that Moore's law rely on, such as Bennett's theorem, which describes if you increase the frequency of the system and build the transistor smaller and smaller, you can actually more cost effectively fit on the chip and then perform computation with higher performance. But that hit the limit. It turns out you cannot increase the frequency furthermore without introducing heat to the system and without consuming too much power. And people noticed that, and then right around 2005, to get around this plateau of Bennett's scaling, we use multi-core, make each core remain the same performance, but putting multiple cores together to use parallelism. So decades of really amazing trend of increasing computational power in classical computers are really slowing down. And in real life, all exponential growth cannot be sustained. So what is next? Well, the reason that the Moore's law is slowing down, one of the reasons was when you build transistors in smaller scale, you're really exposing your hardware to be very sensitive to very small amount of energy. And at that scale, quantum mechanical properties starts to creep in. And for digital computational systems, quantum mechanical properties are just noise, enemy that you have to defeat. But however, can we harness the power of quantum mechanics when we get to such microscopic scale? The question of controlling quantum mechanical systems is really about engineering a macroscopic quantum behavior. And we learned that atoms at this microscopic scale behaves quantum mechanically, but everyday objects, microscopic scale, like you and me, behave classically, mainly due to decoherence of quantum information to classical information. And we'll talk about that in more detail in a minute. But controlling microscopic scale quantum systems is extremely hard. To give you some sense, a hydrogen atom, for example, is around the size of 10 to the negative 10 meters, and it operates at the frequency. The energy difference between the 1s electron level and 2p level is roughly 2.5 times 10 to 15 hertz. And that also corresponds to the coherence time remaining in the 2p energy level before decaying to the ground state 1s level. It's about 1.6 nanoseconds. So if you just leave the hydrogen atom there, it will interact with the environment. And in almost no time, it's going to natural decay. So if you were to store information, say the occupation in the 1s level representing your logical information 0, and 2p representing 1, then you really have a really tight window for storing that information. So making them useful for computation really requires engineering. And my colleagues at YQI at Shokov, Deverett, and Gervin invented this really macroscopic artificial atom for computing, for storing information. And they realized that with the Josephson junction, which is just two layers insulated by the layer of aluminum insulated by aluminum oxide, in a superconducting environment, the phase information across the two plate can be quantized and used as your quantum information carrier. And the scale of this gadget is electrical superconducting circuit at the scale of 10 to the minus 3 meters. So it's really much more tangible. You can look at it and control with the wire. The frequency is in the gigahertz range. So we can use microwave drives, such as widely used frequency for telecom wavelength, and the coherence time is much better in 300 microseconds. So I won't get to more details about the hardware, but I just want to emphasize that remarkable progress has been made since the theory of quantum computation has been proposed. And if you are really a quantum engineer, you will really think about how to fight off decoherence, which is a natural tendency that reduce quantum information to quantum systems to classical behavior. I spoke about a remarkable progress. This is a timeline that includes some of the industry and academia-based quantum computer prototypes. John Preskill had this notion of noisy intermediate scale quantum devices that house 100 to 1,000 qubits. We really had a remarkable journey from the past decade. This, I believe, was about 2 qubits in a trapped ion system. And this is an IBM quantum computer based on superconducting qubits that I talked about, which was invented here at Yale. This was, I believe, a Google's Sycamore processor, roughly 50 to 100 qubits, based on superconducting qubits as well. These are trapped ions. This is a photonic quantum computer designed specifically for computational tasks called boson sampling, so special purpose quantum computer prototypes. And IBM has this roadmap for building. This is a 300-ish qubit machine with distributed chiplets with quantum and classical communication. Their roadmap said this will be built this year. So we came a long way from 1 or 2 qubits from academia labs to really hundreds or even thousands of qubits built in the industry. Why did I talk about all that? As a brief summary slide, I really want to say we get to ask this question because of a convergence of many factors. There are emergence of computational problems that we believe can be solved quantum mechanically, realizing the computational power in complex quantum systems. I will introduce in more detail in the next part of this talk about what are the quantum mechanical properties that we will take advantage of for computation. Then classical computers have limits, have practical limits, signaled by end of Moore's law. And we also have remarkable progress in the ability to control quantum systems at the individual atom level. All of these seem to happen roughly around the same time in the past 2 decades ago. And it all comes down to the notion of realizing quantum speedup. And I'd like to spend a couple more minutes on defining that notion. So assuming you have a classical, you have a computational test that can be solved with a classical computer, and that's the baseline. If you assume this is the log scale in time to solution, then this really means it will take exponential time to solve on a digital computer. Exponential is a scaling argument. It's a function of the problem size. If you increase the problem size, the amount of time, the number of steps it will take is exponential to the input. Now, theoretically, many proposals of quantum algorithm can solve the same problem with a much better scaling. For example, exponential speedup really means that this will same problem will be able to solve with polynomial time in terms of the problem size. But typical analysis of this theoretical quantum speedup rely on very hard to achieve assumptions. For example, we're assuming that all qubits are perfect, all gates are perfect, then the number of steps it will take can be quantified. In practice, though, I really emphasize the challenge of controlling atoms for computation is fighting against decoherence. So forcing quantum computers to behave quantum mechanically without reducing to classical behavior. This I refer to as the notion of decoherence slowdown. If you have a quantum system with increasing amount of noise, the scaling speedup, in fact, will diminish. With higher error rate, the amount of time to solve the same problem will again approach to the same scaling as a classical computer because decoherence reduces to classical behavior. Field has really converged to an effort to find noise resilient quantum speedup. If you are an algorithm designer, then you will find algorithms that are robust to noise, to errors intrinsically. If you are hardware architect, then you will really build your system with reduced amount of noise. All of these efforts are trying to find practical quantum speedup that you can implement on today's or tomorrow's quantum computer that will preserve some kind of scaling difference. Okay, this is a really high-level introduction of what the field is about and why we're studying this. Next is going to be more technical. So I'm going to talk about the math, the science, and really the engineering challenges in more detail. And finally, we're gonna have a hands-on programming session at the very end that allow you to play with writing quantum programs and potentially running those programs on the quantum hardware that we can access through IBM system. Okay, so classical versus quantum information. This is a busy slide, but I'll explain. When we talk about information, we'd like to really comes down to what is the minimal unit of information that we can manipulate. And that is the notion of bit. It's a binary information, 0 or 1, that you can communicate, you can store, you can manipulate. That represent the fundamental unit of information. And when we say information, it's an abstract notion, but we oftentimes also talk about the information carrier. What is the medium that we store or control information? And it can be any ordinary object like the color of a ball. For example, red represents for 0, blue for 1. Obviously, there are other colors as well, but it's nice to discretize it to values, and to work with them is much cleaner. When we talk about logic, which refers to the transformation of information from one state to another, for example, mapping back and forth between zeros and ones, it's governed by Boolean algebra. And it might not sound really interesting when you have just one bit, but if you have, imagine, 1,000 or 1,000,000 bits, then it's really an art to design how you can transform from one bit string to another bit string with minimal number of operations. So that's Boolean algebra. Quantum information is can be analogously defined. The fundamental unit we call quantum bit or qubit also stores information about the basis 0s and 1s. But different from a classical bit, a quantum bit can store information in a linear combination. For example, this quantum state that I wrote in this notation called the direct notation can store information which is a weighted sum of both zeros and ones, alpha 0 plus beta 1. And when you store this information in a information carrier, a quantum system, reading the information out of the quantum systems is called measurement. And this process will result in two probabilistic outcomes, either the 0 state or the 1 state. And the probability associated with the outcome is determined by these coefficients alpha and beta and the relative difference between the two. So I had the proportional two. We'll make this more concrete, but you can imagine a quantum bit, instead of storing just the zeros or ones, it will store the two numbers, alpha, beta, inside and transforming between two quantum bits, or the logic, or quantum logic, is then very conveniently described by linear algebra, because you can just put the two numbers in a vector, and transforming between vectors are matrices. So we'll talk about that in more detail. At this point, you might wonder, well, isn't this just a combination of zeros and ones probabilistically? And to really emphasize the difference between a quantum bit and random bit, it's more subtle. But I'll offer some intuition first and then some more rigorous argument. Randomness is really a notion about uncertainty, something I'm not sure of. It's like putting a bit in a box, and I forgot about what I put in there. And then the best way to describe what's in there is use a random bit because of uncertainty. And however, if you put in a red ball, it will come out a red ball. If you put in a blue ball, it will come out a blue ball. And the probability really depend on your prior information about what is in there. So how different is this to this read information from a quantum bit that give you probabilistic outcome? Well, okay, I will get to that in the next slide, but let me make this definition of quantum information more rigorous, and then we'll be able to explain the different properties of it. So more precisely, a quantum state really stores two complex numbers. Alpha and beta can be complex numbers, and it's a two-dimensional complex vector. For simplicity, for now, for a second, let's assume it's real numbers. But for example, 0.6 or 0.8, then if you plot this two bases, 0, 1, as two orthogonal components, then this state is really a vector with x component 0.6, y component 0.8. A quantum state needs to be normalized because when we measure this quantum information, the probability of getting a 0 state is alpha norm squared, and the probability of getting the 1 bit is beta norm squared. And for probability to work, you better sum to 1. So this normalization constraints put some relationship between alpha and beta, and some special common quantum state that we use often is the plus state and the minus state, which is a really uniform linear combination between 0 and 1. And this is really a linear combination, but with a negative sign. So if you look at these two vectors, they are also orthogonal. And the decision about what is the computational basis definition of 0, 1 is really arbitrary. In other words, you could think of this plus as your new 0 basis, minus as your new 1 basis, and perform computation using these two bases as well. So in other words, you can write this as alpha prime plus beta prime minus without a problem. We'll use that property in a second. But I also want to mention some convenient representation of a single qubit geometrically. Because this is two real lines, it can only describe real combinations, real coefficients in actual quantum system. These are complex numbers. Each complex number is two real numbers, so it really is 4 real numbers, and it's really hard to visualize 4 real numbers in 3D or 2D. So luckily, we have the constraints that they are normalized. So minus 1 degree of freedom, this is really just 3 real numbers. Furthermore, there's this property that global phase does not matter. If you multiply this quantum state by some phase factor, when we say phase, it's really a complex component e to the I phi for some real number phi. These two quantum states, even though you can write them differently mathematically, they are physically indistinguishable. So there's no physical measurements to the system that you can make to differentiate between the two states, other than zeros and one that are orthogonal, you can distinguish very easily. So removing another degree of freedom, in fact, the two complex numbers for this pure quantum state can be represented as two real numbers. And the way you do that is to force global phase to be factored out. So the first number can always be a real number. The second has the real and the imaginary component. Forcing the normalization constraints, remove 1 more degree of freedom. So you can really describe fully this single qubit quantum state with two real numbers, A between 0 and 1, and theta between 0 and 2 pi. So we like to visualize real numbers in a line between zeros and 1. I purposely drew this vertically to motivate the next visualization trick. But to visualize this angle theta between 0 and 2 pi, we can use a disk. So in other words, you can actually visualize a quantum state on the surface of a sphere. The height of, or the latitude of where your vector is really determined by this real number A, and the longitude of where you are on the globe is determined by theta. So with these two real numbers, you can find a unique point on the surface of this globe. And in fact, this is how we visualize a qubit. 0 state is pointing up, 1 state is pointing down. So it will take a while to get used to this, because we're used to having orthogonal vectors having 90 degrees on pictures, but in this representation, they are pointing in opposite direction, the two orthogonal vectors. And then this is the computational basis, zeros and 1. You can represent this as two coefficients to find the location. You could also, as I said, view plus and minus as your basis So you can define an axis pointing at the x-axis, and then a disk perpendicular to that axis. And in fact, this is because plus is exactly the x-axis, minus is the opposite of the x-axis. We will do more practice on the visualization of block sphere in the programming session coming up. Next up is the notion of quantum measurement. And I'd like to invite you to think of quantum measurement as a projection. So I talked about the computational, the vector space that quantum states live in. If you have, in the most general form, little n number of qubits, then it really is a very large space for storing all the complex numbers, which is a 2 to the n dimensional complex vector space. And a measurement in the most general form is just a projection of this complex vector onto some subspace. And the different measurement outcome, let's say there are m of them, is basically a orthonormal decomposition of the complex space into direct sum of the different subspaces. Each subspace the subspaces are differentiated by the measurement outcome. Let's say you will get measurement outcome 1, 2, 3, all the way to m. So if you perform the measurement and then learn that the measurement outcome is, say, r between 1 and m, then you know that the quantum state have really projected onto the subspace H sub r. In this picture, I try to illustrate this with a simple example. If your quantum state is alpha 0 plus beta 1, let's assume I'm performing this measurement to measure whether it's 0 or 1. Then let's call it basis 1. Then I will project, and it will get into measurement outcome 0 or 1. That's the two different subspace determined by the coefficients, which correspond to blue or red on the projection. One could also think about projection in the another basis. Let's say the plus and minus. Because these are just vectors, you can rewrite with different linear combination, alpha prime plus state plus beta prime minus state. And performing the measurement in these spaces is like a projection in the other direction. It will tell you if it's plus, which is red, minus, which is blue. So I'd like to invite you to think about measurement as different ways of reading the information out of the quantum system. Because of this mathematical description, there are three main points that I want to emphasize about quantum measurements. The first point is the intrinsic randomness. So the measurement event is inherently random. It's truly random. It's not the pseudo-random. It's random even if you're given the full information about the quantum state. So you know mathematically that it stores alpha 0 plus beta 1, but if you perform the physical experiment, it's going to be generating random outcome. There's the irreversibility property, which says the measurement operation is really a projection into the subspace. This is an irreversible process. You collapse the quantum state to the associated subspace, for example, either 0 or 1, and there's no way to reverse that physically. Because of this projection, you can also intuitively understand this non-commutativity, right, property. If you are doing two measurement operators in sequence, the first mesh, and if these two operators don't commute, which means that measuring operator A influences the outcome of a subsequent measurement B. And this is also why people refer to the probability from quantum measurement as non-commutativity or non-commutative probability. Okay, so another property that I want to introduce is the notion of entanglement. Because of this linear combination of states, you can in fact create a new notion of shared state. What I mean is, imagine you have two qubits, and the possible states that can live in is four different combinations of zeros and ones. So 0, 0, 0, 1, 1, 0, or 1, 1. And you can specify arbitrary linear combination of the states as long as you satisfy the criteria for being in a valid quantum state. This is a valid quantum state. It's a equal superposition between the 0, 0 and 1, 1 basis. So what would happen if you have this system, and if you perform measurements in any one of the qubits and don't care about the other qubit, you will always get a random outcome. The probability of getting the red or blue, 0 or 1, is determined by the relative proportion between this coefficients and this coefficients. If you look at 0 for the first qubit, it's 1 over root 2, 1 is 1 over root 2, so equal probability of measuring 0 or 1. Same thing for the second qubit. Because you can also rewrite the same state into uniform superposition of plus plus and minus minus state, I can in fact perform measurement in the plus or minus basis also. For example, for the second qubit, and I look at this coefficient, it's 1 over root 2, it's 1 over root 2. Again, a 50-50 chance of getting red or blue. It's also to say that you don't get any information out of this system. This is obviously not just two random bits, but doing measurements or reading off information one qubit at a time does not actually get the information. The information is not stored in any of the individual qubits, but as correlations in the entire system. We can see that by looking at what would happen if we measure simultaneously in the same basis for the two qubits. For example, I agree that we will all measure in the 0 and 1 basis, and on both qubits, then the outcome will be red and red for 0, 0 with half probability, or blue and blue with half probability. So in other words, they are always the same kind of correlation in the measurement outcome. And in fact, when I say you measure them simultaneously, you don't have to measure them simultaneously. One can measure this and then wait a really long time and measure this. But you will know that because I measured the first qubit and turned out red, I immediately know that my next measurement for the second qubit is going to be red. Yes?
So what's the difference in between measuring one after the other and getting both red and measuring one after the other getting different?
There's no difference in terms of the physical experiment. It's just the amount of information that you gain, whether you, so in other words, there's no communication between the two parties, so it doesn't really matter whether you do it simultaneously or one after the other. Okay.
But what you immediately before that, you stated that in the first part of the slide, you stated that we could measure them and get random outcomes.
Yes.
And now we're saying that we can measure them and get the same outcome.
So the difference is whether you measure in the agreed basis. Okay. So that's a really good point. If I don't agree in different bases and I just pick basis, the favorite basis that I like, and it turns out that I measured the first qubit in the 0, 1 basis and the second qubit in the plus minus basis, then they all turn out to be random, 0s and 1s. And another way to think about this is if you look at only the subsystem and don't care about the other party, you're gonna get 50% of red, 50% of blue. Information is really about the correlation between the two, but not really the distribution that you measure each outcome. So entanglement is a kind of information encoded non-locally. That's because these two qubits could be physically really, really far away. And information is stored as a kind of correlation. But people would argue, well, is this just shared randomness? Is this just random correlation? And without getting into too much detail, I'd like to mention there's a physics experiment that we can do to distinguish whether it's really a random correlation between the bits or it's shared entanglement. In other words, if you allow two parties, say Alice and Bob, to share randomness. So they prior to this game, they flip a coin and they have this random bit, hold on to this random bit, versus if they had two entangled qubits. It turns out they can accomplish a computational task with different success probability. Okay, so the goal is to jointly compute something. Alice gets one part of the input, Bob gets another part of the input. The goal is to compute the end of the two bits, X and Y, but then output in a really correlated way. You are asking if Alice can output A, Bob can output B, so that when you combine the two with an XOR operation, it's equal to the end of the two inputs. So the assumption is that Alice and Bob don't talk to each other. They don't share X or Y with different parties, but they do share either randomness or entanglement. The best strategy they can play to achieve this is through a randomized algorithm that will get you at most 3/4 of success probability. But if you allow qubits, entangled qubits, you can achieve this with approximately 85%. So this is really a beautiful experiment to illustrate that entanglement can be used as a resource. And in fact, after it's been proposed, first by Bell in '64, and then later formalized with this strategy by these names, and then realizing physics experiment by Aspect et al. In early '80s, people have demonstrated that entanglement can really be used as a resource. And by the way, this was the Physics Nobel Prize recently. Okay, so I'd like to finish this sort of mathematical component of this lecture by looking at logic again. since we're doing computation, we care about transformation between quantum states. And I really mentioned that if you store quantum information in vectors, then linear algebra will be really helpful. And it's physical transformations, physically realizable transformation will transform one valid quantum state to another valid quantum state. When I say valid, alpha beta has to satisfy some conditions, gamma delta has to satisfy some conditions. So physically realizable transformations are only a subset of matrices that you can apply. And in particular, if you want to make sure the qubit stays valid in terms of the quantum state, then we really need unitary matrices, which defined as the inverse is equal to the conjugate transpose of the matrix. We can prove it by going through the conditions for valid transformation of valid quantum state to another valid quantum state. But working with unitary matrices all the time is really hard. And one thing we learned about building classical computers is to digitize things. So we'd like to have a subset of operations that maybe can implement arbitrary transformation. And remarkably, we can do that over here as well. A sort of claim about computational universality is to say we can define a subset of operations to implement arbitrary transformation. Proving this is more involved than what we can do today, but I also don't want to miss out this very interesting point of how transformations are implemented in real hardware with only a subset of operations. So I'd like to invite you to work on this exercise with me to prove a claim that any single qubit transformation can be implemented by rotations, and in particular, two types of rotations: rotations about the x-axis and rotations about the z-axis. Again, in the block sphere, in the sphere representation. So I said a quantum state, a valid quantum state, is a vector pointing to the surface of this sphere, represented by two real numbers. Imagine you can build hardware that will implement rotations about the z-axis, which will rotate in the xy plane, parallel to the xy plane, or you can rotate. Oh, this is actually a y-basis rotation pictorially, but you can imagine a corresponding x-axis rotation. So if I say an arbitrary single qubit transformation, then you would think, well, it's not just rotations about x or z axis. It could be rotations about any axis. Let's take a minute or two to think about how do you implement an arbitrary axis rotation about arbitrary angle by rotation of these two axes. Maybe you can also talk to your neighbors, and we'll discuss the strategies together. Yeah.
I was gonna say that I believe using x and z rotations, you can like rotate the z-axis onto your original rotation axis.
Great.
And then another z rotation is just your like the original transformation.
Great. So let me repeat. The strategy is to rotate the z-axis to the original axis that you want to rotate through a series of z and x, and then rotate around that axis first before you move that axis. This is a great strategy. Can you elaborate on how would you move an axis, z-axis, to an arbitrary axis with x or z basis rotations? Yeah.
I mean, since you can rotate it full 360, since you can rotate it the full way around the sphere, you can get to any axis that's going through the two poles, which means you can technically get up to any point on the sphere.
Okay, so this is just an illustration of a finite or a subset of operation and implement a wider range of operations if you concatenate different operations in sequence. And more generally, in fact, we don't prove it here, but Hadamard gate, which you will learn in the hands-on programming exercise, together with the z rotations about 45 degrees, can implement any single qubit transformations, just that two gates alone. And what's more interesting is that you can use single qubit gates plus two qubit gates to implement arbitrary transformation on any number of qubits. I gave an example of a 3-qubit gate here. This is a notation in a circuit model where the black dot is a control, the circle is a target. It says if the two controls are both 1, I will perform a NOT or X, a flip between zeros and 1 for the third qubit. And this gate can input arbitrary linear combination. It will do this control NOT operation in superposition to all the bases. And in fact, you can find an equivalent computation logic circuit with only single qubit and 2-qubit gates. In particular, it's the Hadamard gate and the T gate, which is another name for the rotation about 45 degrees with a 2-qubit control NOT gate. But I want to emphasize that having a universal set doesn't mean that we should build a quantum computer with only these few gates. Maybe we also think about redundantly universal instruction set. For example, with the goal of implementing a more efficient circuit with fewer number of operations. If you allow more redundant instructions in your tool set, potentially you can implement a circuit with fewer gates. And for example, a top-lead gate can be implemented with a different number of gates if you change the gate set. And the question about circuit synthesis and quantum compiling is really for finding a circuit or a program, or in other words, a sequence of quantum gates together with measurements that will implement your desired transformation, say specified by unitaries or different instructions. Most of the technical contents we have already introduced. Now let me just go through some of the high-level points of sources of quantum advantage and what are we looking for when we design quantum algorithms. One notion of quantum parallelism was really essential in realizing quantum speedup. If you have lots of quantum bits, they really encode information in a very large complex vector space. In particular, I said it's a complex vector space of dimension 2 to the n. This is essentially a tensor product of the individual two-dimensional complex vector space. And the space, the giant vector space is spanned by the bases, binary bases, 0, all 0, all the way to all 1 for the qubits. But they can live in superposition of any of these states. And a nice way to represent the superposition is to write out all of the coefficients or superposition as different paths. For example, a quantum gate can really represent it as transitions between states. If your input is alpha 0 plus beta 1, let's write that as 2 nodes. A unitary transformation for 1 qubit is a 2 by 2 unitary matrix, and the matrix element correspond to the transitions between the input and output. So after applying this gate, you get the quantum state alpha prime 0 plus beta prime 0, and you can calculate what alpha prime beta prime is by multiplying this unitary matrix on the vector, which can be represented in this pictorial way. Transition from 0 to 1 is really using the matrix element U1. So alpha prime has also contributions from the original 1 state, which is specified by the beta coefficients and the matrix element U2. In other words, mathematically, alpha prime is just a sum of the paths that go into this node, which is U1, the edge, times the starting point alpha, U2, this edge, times the starting point beta. So transformations can be thought of as transitions on this diagram. This is called the Feynman path diagram. And if you are given a quantum circuit like Hadamard transformation on each qubit, which the Hadamard transformation is to branch out from 0 to 0 plus 1, and then 1 to 0 minus 1. So if you concatenate 4 H gates on each qubit together, you're really branching out exponentially to all of the states. So you can pictorially see how fast this number of paths grow. When you think about computation, it's really about transformation of input states to output state. And here we listed all the possible inputs, all the possible outputs. And it seems like this quantum circuit, which contains only 4 gates on the 4 qubits, is able to reach all of the output states at the same time. So essentially, it's calculating what is the input 0 transformed to the very end, all at the same time in superposition. So many people like to think about this as a massive parallelism intrinsic to quantum computation. We know measurements is the way to get information out of the system. So the whole picture is not just about parallel branches, parallel computation. It's about how to get information out of this massive parallelism. And for example, if you perform measurements to this quantum state, you're just gonna get the information, get a sample of the outcome with uniform distribution, you have to repeat exponential number of times in order to know all of the output from this parallel computation. So the art is really to narrow down the number of outputs so that when I perform quantum measurements, I will reach the desired output with high probability. So in order to leverage this quantum parallelism, we really need to design the circuit so that all of the computational paths will hopefully converge to a desired output state, and so that when we measure the output, it will come out with high probability. So leveraging quantum parallelism is all about designing massive superposition, but also how different paths interact. And in particular, when you have positive coefficients and negative coefficients meeting at a point, they cancel because we add those contributions from different paths together. In this picture, which is a tool that my students used, generated, you can access through this GitHub link, is to help you visualize what are the coefficients in different computational paths, how they evolve, and colors represent positive or negative values. And if you see two blue line meeting an orange line, they cancel. So the final coefficient for the 1-1 state is 0 in this case. Final coefficient for 0-1 is a 1. So when you measure the quantum system, you'll get 0-1 state with 100% probability. Similarly, you can create examples for different circuits that will interfere differently. So I'm just gonna jump through some of the high-level points of quantum algorithm design and system design, since we're running out of time. So we talked about the fundamentals of quantum computing, but really, how do we realize these quantum speedup depends on how we implement these algorithms in practice. And I want to just say that there's a huge gap between the number of qubits and number of operations that we can do on current quantum hardware compared to the size of the circuit that's needed to implement these algorithms. And unfortunately, I won't go into more detail about this strategy for protecting quantum systems against decoherence through quantum error correction. But you can imagine, in order to perform computation fault tolerantly, you really need to overcome the inevitable loss of information to the environment through decoherence. And the strategies was to use quantum error correction codes. And the second strategy is to design software stack and hardware component to work together. For example, the software can optimize the quantum circuits, simplify the circuit for hardware to run so that it's more efficient, more robust. Software can also help correcting errors in the quantum error correction procedure. But the whole process, I'd like to draw a parallel with the development of classical computers. So after the invention of vacuum tubes in the early 1900s, and then development of transistors, integrated circuits, all the way through modern computers, it took us a long time to get there. In the 1960s, we have this IBM system 360, which is really a remarkable system with modern the architecture looked like a modern computer. And we have IBM quantum computer. This was a few years ago now. They both occupy a big portion of the room. And the question is, well, this time around, can we build a practical quantum computer sooner than decades or even 100 years of technological advancement? I believe the answer has to do with, in fact, leveraging what we have already built, digital computers, and also the experience of building digital computers to help us building quantum computers altogether. Well, so let me end by a more positive note on what we have learned so far about emerging applications in all areas, and we are hopeful that after discovering more opportunities to find quantum speedup, we'll be able to understand how to build our quantum computer to tailor to these applications better, and realizing that